So today we will learn about local and global time and state in distributed system. By the end of this topic, we should understand why time synchronization is important and how distributed system contain a consistent view of events. So this session focuses on how distributed systems handle and the system state. Since multiple computers work independently, they need mechanisms to coordinate their clocks and maintain consistency. So the time plays the vital role in distributed systems. It is used for transaction, ordering, database consistency, and auditing. However, because computers have different clocks and communication delays, physical time alone cannot always determine the correct order of events. That's why synchronization and logical clocks become necessary. So each process has its own hardware clock, but these clocks can drift apart over time, causing clock skew. To improve accuracy, systems uses coordinated universal time or UTC, which is based on highly precise atomic clocks. So coordinated universal time. So UTC is the global standard for measuring time. It's synchronized using atomic clock and is distributed through GPS satellites and other time services. This provides a common reference for computer around the world. So this is called as clock skew. This figure illustrates how different computer clocks gradually drift apart. Even if they start together, small timing differences accumulate over time, making synchronization essential. So Christian's method, the Christian's algorithm synchronize a client's clock with a server by measuring the round trip delay. While simple, it depends on a single server, which can become a bottleneck or a single point of failure. So here, network time protocol. So NTP is the most widely used protocol for synchronizing clocks over the internet. It uses multiple servers, statistical filtering, and hierarchical layers to provide reliable and accurate time synchronization, even when some servers fail. So here the NTP synchronization network. This diagram shows the hierarchy of NTP servers. Primary servers obtain time from highly accurate sources, while secondary servers synchronize with them and distribute time to clients. Here we see how two NTP peers exchange timestamp. These timestamps helps estimate network delay, clock offset, and so that each system can be accurately adjust its local clock. So logical time and logical clock. In distributed system, physical clocks are always not enough. Lamport introduced the idea of logical time, where the order of events is determined based on the causality rather than the actual clock values. Happened before relationship. The happened before relationship defines the logical ordering of events. Events within the same process flow. Execution order, sending a message happens before receiving it, and this relationship is transitive. So next, logical clocks. Lamport logical clocks assigns timestamp to events. Each process increments its counter before an event. And message timestamp help receiving processes update their counters while preserving the happened before order. The events in three processes. This example illustrates event occurring across three processes. It helps visualize how communication creates dependency between events in different steps systems. Lamport time step. Applying Lamport algorithm gives each event a logical timestamp. This timestamp maintains the correct sequence of causally related events even without synchronized physical clocks. So next one is the vector timestamp. Vector clock improves on Lamport clocks by keeping a timestamp for every process. This allows us to determine not only event order but also whether two events occurred independently. Global states. Global state combines the local states of the process. To correctly capture the time's overall conditions, the collected states must form a consistent cut that respects the happened before relationship. Detecting global properties. This figure demonstrates how global properties are detected by examining consistent global state across multiple distributed processes. So consistent and inconsistent cut. This diagram compares consistent and inconsistent cuts. A consistent cut includes all classically related events, while inconsistent cut may include a message received without its corresponding send event. So next is Chandy and Lambo snapshot algorithm. This algorithm captures a consistent global state without stopping system execution. It uses marker messages to record processes states and communication channels states. So initial processor state. This example begins with two processes in their initial state. Before taking a distributed snapshot, it sets the state for understanding how the algorithm works. So finally, snapshot algorithm. This figure shows the execution of the snapshot algorithm. Marker messages travels between the processes, allowing each process to record its states consistently and produce a correct global snapshot of the distributed system. So thank you.